So this is my lap 5, and I did mine on a falling
All right.
3, 2, 1, drop.
static equilibrium.
Wow, did you see that?
And the physics principles were Newton's second law. Force
All right.
equals maximum
3,
acceleration
2, 1,
with gravitational force, so F equals
Wow, did you see
mass
that?
times gravity. And the previews of
All
the
right.
result,
3,
our
2,
model
1,
successfully
drop.
predicted the complex path
Wow,
observed in the experiment. Background: the system is the spring in this case, and it's just being released from being held up. And the gravitational force is mass times gravity downward. And then in this experiment, there's tension because slinkies are tension springs. And at the beginning, the tension of the slinky holds the bottom up. So that's why you see the bottom stay stationary for a minute before falling once the top of the slinky catches back up. And then the net force, F net equals tension plus F grav, and then F equals ma, which is Newton's second law. And then initial conditions and system setup, our mass was 0.25 grams. The initial position was this vector. Our initial velocity was 0 because it was being held stationary. And then all of these values were measured from the video analysis and tracker. And you can see up here, these are my tracker results. And then here is my initial conditions written into the code. System is the slinky, the surrounding is the Earth's gravitational pull. So coding the model. So the method we used was like Euler, where it does all of these calculations over and over again, so like a loop. And then we had 2 phases. In the first phase, from 0 to 0.76 seconds, where the bottom is stationary even though the spring has been released. The top is fixed and the bottom is suspended by tension. So the net force is 0 on the bottom of the coil because it remains stationary. And then phase 2 is the free fall. And this is from 0.7 seconds to 3.68 seconds. And this is when the entire slinky collapses under gravity, and the bottom of the coil will like almost move upwards until they collapse and then they fall together. And then results, and what does this mean? The slinky collapse phenomenon was shown because at the beginning the bottom didn't move, but the top of the slinky moved downwards onto it. But since we were tracking from the bottom, you can see that it's stationary, and then it will start to move together once it collapses. So it remains stationary for 0.6 seconds. And then this shows that there's a wave propagation speed because, again, it was stationary. And then the numerical validation, we successfully, with our method of looping through the same calculations over and over again, captured a somewhat accurate model of this complex system. And then the key similarity between the real and the computational model was that the overall shapes match. They show the bottom coil remaining suspended while the top collapses, and the key difference is of the trajectory smoothness. So the computational has a clean, straight path, but the real world shows the wobbliness of the actual slinky. And sources of error, it could be like pendulum motion, like this. In the video, you can kind of see this swing moving back and forth. Air resistance, an imperfect release, and then internally there could be some spring friction. What if we used a heavy slinky? How would the results change if we doubled the mass? So the same time delay would occur so the hover period would remain 0.76 seconds. And that's because wave speed depends on tension and mass per unit length. So the collapse is determined by the length of the slinky and the material of the slinky, not the total mass. So a heavier slinky would fall with more momentum and hit harder, but the hover period would remain the same. Thank you.